Okay, so this is an introduction to parametric equations with a little bit of calculus in it. So parametric equations are a way of describing a curve in the xy plane because we mostly talk about functions in calculus, where y is a function of x. But there's a lot of curves that are not functions. In other words, it's a curve in the xy plane, like maybe a circle. It's not a function because it doesn't pass the vertical line test. But it's still a curve. It might be the trajectory that a particle follows if it's traveling through the xy plane. It's still a curve that we would want to talk about. So for that reason and many other reasons, sometimes we want to describe a curve as, instead of a function, whether it's a function or not, because it might not be, we describe it as parametric equations. So the way this works is, instead of having a single equation that involves x and y, we have two equations and we have a third variable. So x is a function of t and y is a function of t. And when we graph this, there's no t in the picture. There's an x and a y-axis like normal. T is not really in the picture. T is just this hidden variable that we call the parameter. So here's an example and just how graphing works when you do this. So I chose a particular function for x and a particular function for y, and plugged in some values of t. So I just chose some kind of obvious values, and for each value of t, I plugged it in here to figure out what x would be, and here to figure out what y would be. So, and the way graphing this works is I would plot those points, and basically we can ignore t. So, okay, the first numbers are kind of big, and I didn't want to draw a picture that high, so I skipped the first point. But then here's 4, -2, so that's a point. So this is, right, this is t equals -2. This one is t equals -1. This is t equals 0. I'm just noting the t values because otherwise there's no way of looking at this picture and figuring out what t is. And that kind of matters for understanding the curve. So this is t equals 1, and this is t equals 2, and t equals 3 is another point that I just didn't draw because the numbers were too big. So before I drew those values of t, it might have been, like, one might think that maybe the dots are connected in this order, like it just makes this kind of shape. But actually it goes from here to here to here to here to here. And by the end of the video, I would like to sketch the curve, but I'm not quite ready to do that. But what we just said is at least a very vague picture of what the curve must look like. Somehow it has to connect the dots in this order. It's got to go like this. It makes a swirl. In particular, it would seem, like, assuming that it just sort of smoothly goes through these points in some order, it would seem that this curve must cross itself. Like it comes up like this, and then down, and then it's crossing through the same space. So one of the first things we're going to do is show that this curve does cross itself, and we're told at the point where it does. So what does this really mean? What this means is there's two different values of t where x and y turn out to be this point. So we're going to show that the curve does indeed cross itself by finding the two different values of t that give me that point. And it's not so hard. So I'm going to find two solutions t where t squared equals 3 and t cubed minus 3t equals 0. So I can pick whichever one of these, well, okay, it's going to be this one. because I can pick whichever one of these I want to solve. And yeah. Anyway, I'm making this harder than it needs to be. So t is plus or minus 3, and of course, if f of 3, that's my x, that gives me 3 g, or sorry, I meant f of root 3. G of root 3 is this. If I plug it in, of course, root 3 cubed, that's, because these two things are 3, so this is 3 root 3 minus 3 root 3, which is indeed 0. And we can check f of minus root 3, the other solution, also gives me 3. And you can check that this also gives you 0. So these are two different values of t for which x is 3 for both of them and y is 3 for both of them. So now that we know that it goes through this point. And this is when t is root 3 or negative root 3. So root 3 is about 1.7, so it sort of makes sense here. Here's negative 2, and then what this is saying is that when t is negative 1.7, so it's like on my way from negative 2 to negative 1, at some point I cross through negative 1.7, and I'm at that point. And then likewise, when it's somewhere in between t equals 1 and t equals 2, then I'm at positive 1.7, and that's when I cross through that point again. Okay, anyway. So, like I said, this is going to involve a little bit of calculus, so let's talk about tangent lines. The slope of the tangent line is this thing that we call dy over dx, which is supposed to be approximated by a small change in y divided by a small change in x. So this is like I take 2 points on the curve that are very close together, and I do the difference in the y coordinates divided by the difference of the x coordinates. I would like to involve t in this somehow because I'm talking about parametric equations. So I'm just going to divide the top and bottom by delta t, like say my 2 points that I'm using to calculate delta y and delta x. Those correspond to different values of t if I'm on a parametric equation. So I can do that. And of course, this thing on top this is basically what we would call, or this is approximately in the limit for very small values of delta t and delta y. This is approximately dy over dt. And then the bottom is, whoops, my x looks kind of bad. The bottom is dx over dt. And these approximations are equal in the limit, when you take the limit as the, delta t goes to 0. So actually, what I'm going to put in the box is dy over dx equals this. So that's what this says in the box. Of course, that only makes sense if the denominator is not 0. So this gives us a way of finding the slope of a tangent line. Of course, in the beginning, I was saying that x is f of t and y is g of t. So when I write this, another way of writing it is, this is just g prime of t. Like y is g of t, so when I say dy over dt, that's g prime, and dx over dt is f prime. By the way, you can have a vertical tangent line. A vertical tangent line is when x is not changing, so you're not moving at all horizontally, but you are moving vertically. So your dx over dt is 0 because you're not moving at all horizontally, and your dy over dt is not 0 because you are moving vertically. Of course, a vertical tangent line has an undefined slope, and this is exactly when you would be dividing by 0 if you tried to use this formula. So this is indicative of a vertical tangent line. Horizontal tangent line is the other way around. That's when you are moving horizontally, but you are not moving vertically. Okay, so going back to our previous example, let's find some horizontal tangent lines and vertical tangent lines. So for a vertical tangent line, that's where I want dx over dt to be 0. So dx over dt, for us, that would be 2t. So that would only happen when t is 0. Of course, I guess technically we should check that dy over t is not 0. So let's check that. dy over dt would be 3t squared minus 3. And indeed, that is not 0 when t is 0. So the value t equals 0 does indeed give me a vertical tangent line. And looking at the picture, maybe that makes sense, because I know that I sort of go like this. So this point sort of seems like a transition where as t starts at -2 and slowly increases, I'm moving to the left, and then I reach this point, and I have a vertical tangent line. I'm moving like straight down, and then I start moving to the right instead. So like maybe a clearer picture is starting to form of what this shape is ultimately going to look like. Anyway, let's keep going. Horizontal tangent lines, that would be where dy over dt is 0. So we already found dy over dt. Set that equal to 0. I can solve that real quick. T is going to be plus or minus 1. And technically, to verify that it's truly a horizontal tangent line, we should check that dx over dt is not 0. Dx over dt was 2t, and that is not going to be 0 at either of these values of t. Oops. Writing a little low there. So that's happening when t is at -1 and +1. So these are horizontal tangent lines. So maybe even more clear picture is starting to form. It goes like this, and then probably this is the highest point that it reaches before it starts going down again. And then this is the lowest point that it reaches before it starts going up again. Okay. And, oops, almost forgot. Let's find the tangent lines at this point where it crosses itself. So the tangent lines at this point 3, 0. So what I want is t values, and I know that this happens when t is the square root of 3 and also when t is minus square root of 3. So I'm just using this formula. I am using this formula. dy over dt divided by dx over dt. And that is, oh, I'm all over the place. So derivative of this over derivative of this. So 3t squared minus 3 over 2t. And we're just going to plug in root 3. So, okay, so this is 3 times 3, so 6 over 2 root 3. So that's 3 over root 3. In other words, this is just root 3. At the other value of t, we get, well, I'm just plugging in negative root 3 here. So this is still going to give me the same answer on top. It's still going to be 6. But the bottom is now going to be negative 2 root 3. So this is like the same as what it was, but negative. And yeah, so if I look at the instructions, it said find both tangent lines. So let's actually find equations for these tangent lines. And by the way, I'm just going to use point slope form. When t is root 3, we get, so they both go through this point, so y minus 0 equals, okay, the slope was positive root 3 at this value of t, so root 3 x minus 3. And then this is the other one. Okay. While I'm at it, yeah, let's see. I am disorganized. Here we go. Let's talk about the second derivative. So the second derivative, I'm using this notation. This just means, well, it's the derivative of the derivative, at least when y is a function of x. We just take the first derivative and then we take the second derivative. But things get a little bit funny when we have parametric equations. So what this really means, it's the rate of change of the slope of the tangent line with respect to x, which is like saying if I change x a little bit, how much does the slope of the tangent line change? And we're sort of going to do this the way we did the first derivative, but so what does this mean? This is the derivative with respect to x of dy over dx. And how do you do the derivative of something with respect to x when x is a function of t and whatever you're doing the derivative of is also a function of t? Well, we did that once before when we were taking the derivative of y with respect to x. We did the derivative of y with respect to t, and then we divided it by the derivative of x with respect to t. So what I want to do now is I want to do the derivative of this thing with respect to x. So I do the derivative of it with respect to t, and I divide by the derivative of x with respect to t. And I end up with this. It is not the same as what one might guess. This would be the easy guess, which is that I just do the second derivative with respect, the second derivative of y with respect to t and divide it by the second derivative of x with respect to t. It's not the same thing. So here's how we do it. Yeah, right. By the way, the question is find values of t where our curve, and this is the same curve we've been working on throughout this video, is concave up and concave down. Of course, concave up just means second derivative of y with respect to x is positive, and concave down means it's negative. So this is a basic question about the second derivative of y with respect to x. So that's why we're finding it. Well, so I'm using this. Let me fill in this bracket because, let's see here. Yeah, if I look around at all the work I've already done, I can find it here. Here's dy over dx. Here's where we found it before. So like that. Okay, here we go. The bottom is easy to fill out. The bottom is dx over dt. I've got that in a number of places. That was just 2t. And of course, that's literally just the derivative of this. It's the derivative of x. So the bottom is easy here, 2t. On the top, it's not so hard, but I do have to use the quotient rule. It's the derivative of this thing with respect to t. So low d high minus high d low over low squared. Let's simplify that. Let's see here. (12t squared minus 6t squared plus 6 over, and then this bottom goes with this bottom, so it's going to be 8t cubed. And I guess I can cancel it 2. Oh, yeah, so this makes 6t, and I'll cancel it 2. So 3t squared plus 3 over 4t cubed. Okay, so that was mostly what I wanted to show you. That's how I do the second derivative of y with respect to x. But let's answer the question. The question is where this curve is concave up or concave down, which just amounts to saying when is this positive and when is it negative. And luckily, we can just sort of look at it and tell. The top is always positive because I see t squared and I'm adding a positive number, so the top is always positive. So it's just a question of what makes the bottom positive or negative, and here I have an odd power of t. So when t is positive, the bottom's going to be positive. So this whole thing is positive when t is positive. And it's negative when t is negative because that makes the bottom negative. And actually, I can just answer my question this way. So the curve is concave up when t is positive, concave down when t is negative. So finally, let me draw this picture, and I'll try to, I'm not going to do a perfect job, but I'll try to sort of incorporate everything that we learned. I know that it goes here, then here, then here, then here, then here, then here again, and then here. And what else do I know? I know that it has a horizontal tangent line here, a horizontal tangent line here, a vertical tangent line here. I know the tangent lines here, but those are, maybe well, okay. We can think about this. I'm not going to draw a perfect picture. I know that the slopes at those points are root 3 and minus root 3, and I know that root 3 is about 1.7, so I'm not a great artist, so you're not really going to be able to tell whether the picture that I draw really has a line that's slope is 1.7, but we can think about that as we draw the picture. And we also know that it's, for negative values of t, it's concave down, which is like a graph that has a shape like this. It's curving downward. So the negative values of t are from like -2 to 0. So I could probably guess that it's going to have this shape, but this is what the concavity is telling me, that it's sort of curving downward. And then beyond 0, when t is positive, it's concave up, so it's going to have a shape more like this, like a parabola opening up type of thing. Okay, but like I said, I have way too much to think about, and it's not going to be a perfect picture, but something like this. And let's just say that it goes forever like that. I mean, I do know, like, keep in mind I have these points that I didn't draw in the picture, so 918 is somewhere way up here, so it's sort of a good guess that it just sort of goes off forever in both directions. Anyway, let's call that a good picture.